Okay, welcome back. So in this module is a little bit shorter, but I'll just introduce property-based testing to you. That's gonna be what you do in assignment 3. So it's important you get an overview, but it's a really simple idea, and it's a powerful idea. So I think this is something important for you to have with you after this course. So let's get started. So what is property-based testing? It's a very simple but very powerful idea. And in some sense it's been around for long, this general type of testing. And what it is to combine properties. So properties are pieces of code that express our expectations. So they can act as an oracle. And what the properties do is that they are functions or methods in a programming language, and they take test data as input, and they call the software that you're testing. So they call into the API or the library or the piece of code that you're testing, and then they state what they expect to happen. So this might sound to you like any type of assertion, check, or test in normal automated testing, and in a sense it is. But the key thing is that it's parameterized. So it has a parameter or more, an argument to the property, which is the test data that you're going to use. And by expressing this, so it's a generalization of the normal tests that you write, the concrete tests. And even in my previous hands-on video where I showed you some actual automated testing, it's easy to do this type of testing just by doing a loop and generating the data. So this is property-based testing is a formalization, a packaging of this idea, and the tools that do property-based testing come with some nice to have things when you're doing this type of thing that you didn't see in my example code. So property-based testing is a very simple but powerful idea, and it combines the properties, and this is the key thing, right? So these are pieces of code, small often, that express the oracle, express what should happen when we have data of a certain type, a certain form and shape and so on. And then of course, in order to run these properties, to actually test them against the software, you need test data, right? So in principle, you could get it from anywhere. You could take actual test data. You could look at your manually created test suite and use that data again. But what property-based testing in particular do is to randomly generate test data. And the good thing with random test data generation is that it's very simple to get going. You don't need an advanced tool. You don't need an advanced test data model. Just by going from some basic data types and being able to generate them and putting that into the properties, you can test a lot of things in a lot of different ways. Because a random test data generator will find also the strange test data, the unusual, and thus can help you uncover unusual bugs, unusual states, and so on. So this is the basic idea. Combine parameterized test code, right? So we take our checks and our test code and we generalize it and we turn that into a piece of code called a property. And then we couple that with a data generator. And in the most basic version of the idea, this is a random test data generator. And then you can run the oracle and the test code many, many times because it's fast to generate random test data. This is the power. Key benefits. The properties, as I said, are parameterized, so they can cover very general expectations, almost like laws that must always hold for a big chunk of test data and inputs, right? If, on the contrary to PBT, if we are just writing down our own concrete test cases, then we are limited. We can only generate a few of them. And those examples need to be just examples, like specific cases that we write out. What do we expect when we give this particular input? What do we expect to happen? So in this sense, PBT, or probability-based testing, shares the benefits you've seen in model-based testing. So it's just that the focus in model-based testing is often on behavioral modeling, state-based models, finite state machines, and so on, right? Transitions in these graphs and whatnot. Here, this is a different type of model-based testing, where the model is very simple. It's basically only about the test data. And then you write down there's much more focus on on finding and writing down the general laws, the properties of the oracle. What do we expect the software to do? And in some sense, there was, at the time of these techniques becoming prominent, which is in the last 10 to 20 years, there was less focus on the oracle. You kind of assume that would magically come in from somewhere, and then automated testing was a bit hampered by this. So property-based testing was a good packaging of that idea, and really putting these two things next to each other and putting more focus on the oracle per se, and expressing that as small pieces of general code. Another key benefit that I mentioned already is that random testing is easy to get going with. So regardless of the language, it was so easy for people to take this same idea of PBT and implement it in their own tool, or in their own language, or for their own use case. So random test generation is fairly easy, right? You randomly generate some base types and you put them together into more complex data. So it has a very good bang for the buck. It's easy to understand random test data generation, so it's easy to get going, and it's easy to re-implement. Doing it well can be hard, right? Because for very complex data, like we saw in the previous module, where you have many constraints, maybe on a system level, with a complex system, there are many interdependencies. It will be harder for a random test data generation strategy to hit all of those dependencies by chance, right? So then we might need a more powerful way to generate data. But the same idea holds. Combine simple expressions of your expectations of the oracle in properties, and so that you can run them and test them individually and many times. Actual tools for this also often have very nice features for understanding which test data did I actually try, or did the system try, and when we find a problem. So when a property is violated, it's not true, right? I mean, we expect it to always be true, but the benefit of a PBT tool is when it finds a specific test data where the property is not true. So there might be a bug, or we wrote the property in the wrong way, right? Often randomly generated test data can be too complex, right? By accident, it was very long array of particular values. And then PBT tools can often minimize now this array or this data structure down to something. So it will try to shrink the test data while still violating the property. So this is called shrinking, or size minimization. And it's often not perfect, right? So you cannot find the smallest example that could show the bug, but it's an important feature of these tools, because it can really help you. Because during debugging, if you get a multi-page test data example back, you don't know where is the problem, right? So minimizing it once you find the problem is a key property of these tools. And this part is harder to do if you do this on your own. But it's not super hard, right? You can imagine how you would do it. You basically try to take away things of the data structure and see if the property still is violated. So the whole idea is similar to many existing ideas in automated testing. So just parameterized unit test. This has been around in many tools for a long time, and it shares many similarities. They didn't have the same focus on small properties then that can be tested independently, so that could be a downside of parameterized unit tests. But you know, in essence, you can express this same idea in many forms. I mean, also design by contract, which is a way to specify what do you expect on the input as well as the outputs of a specific function, also had this and related ideas early on. But you know, the idea is still very powerful. So let's look at, this is actually an older version of the original paper, so it's been cleaned up. I think the original paper was in 2001 or 2000 or 2001. So it was by some colleagues here at Chalmers. They are still around. So Cohn was the student of John Hughes, and they developed this early on during his research here. And they call this quick check because they imagine that you can just run a few simple checks on your code with these small properties and get a lot of bang for the buck. And that was true. So the idea, the name of quick check has also been important because you can find a quick check for implementation, and it's called quick check often for many different languages. But this was an important work from the university here. So a very simple example. I take the examples here from this paper, which is also linked and part of the course material. So here's how you think. So the key sort of what can be challenging with PBT is how do you come up with good properties? Which ones should I select? If I don't know, where should I start, right? In this simple example, it's kind of obvious. So here we are going to test a reverse function. So a reverse function takes an array or a list, so some kind of sequence, and when we apply reverse, it will give back the same sequence or array or list, but in the opposite order. So what was before the first element will now be the last element, and vice versa, right? So the second element will be second from last, and what was third from last before will be third from the start now instead. So that's the general idea. So here you can see some general laws that we expect this function to have. So here it's in Haskell syntax, so it might look a little bit different to you, but I'll just show that the ideas are simple. The first row here, the law says, if we reverse a list or array or sequence with only a single datum in it, so a single value in it, then we get back the same thing. So this is something that we expect to always be true. If we give it a sequence of length 1 and we reverse that, we should get back the same sequence, right? So this is obvious. So in this case, this is very clearly true, right? Reverse, and here you see, if you give it something which is the concatenation, xs plus plus ys in Haskell means take the sequence list or array xs and stick the sequence list or array ys onto the end of xs. So it's like concatenating them. Take xs and merge it, concatenate with ys, right? So what we then get, if you think about it, this is true. If we reverse the whole thing now, if we reverse the concatenated sequence or array, that is the same as, do you see it? So this is the last one in y here. So now if we do like this, that will be the first one in the whole thing. So it's actually the same as reversing them separately and switching the order, right? This is what the second law says. And this is always true, should always be true. And then we have the very simple thing that if we reverse the same thing twice, we get back the original thing, right? So if you first reverse a list and then you reverse again, you should have the same thing. So these are three very simple laws. They are not the only ones you can think of, but they are a starting point. And in Quick Check, so what you do is just that you turn these laws into code. And the convention is, in many of these tools, is to add the name prop at the start, or property, right? So we call the first law from above the property reverse unit. So it means unit is something of multiplicity 1, since a basic, it's what it means. And then in Haskell you can express that like this: reverse on so the property takes first x in, so it takes any data, any value in, and then the property will put this value into an array and reverse that, and then it will check the double equal signs that this is the same as taking the value and putting it into a list, right? So this is an operationalization. This is a way in code to describe what the mathematical or general law or property from above is. A way to test this. Take any data, put it in a sequence, reverse it, and ensure that this is exactly the same thing as taking the data and putting it in a list. The second one, now since we have xs and ys in the law, in the second law from above, we also need two arguments to the property. So the property will now take the two actual lists, xs and ys, as arguments, and then it will actually do what's in the law, and it will check that the result is the same thing. So on the left side of the double equal sign, you have first concatenate the lists and then reverse them. And then on the right side of the double equal sign, you have reverse first ys, then reverse the second the x's, and then concatenate them. And then the double equal sign will check that we get the same thing when we do these two different things. So you see now the pattern. The property takes the data in a general form, and then it performs the thing, and it makes a check or a test or an assertion in the end. And then property, the third one, is called rev, so double reverse. And here we take any sequence, array, or list, and we check that if we do twice, we get back the original. Right? So super simple, right? One-liners, or two-liners here. And you see the key thing is that a property is just a piece of code, often short, because you want it to be short, easy to understand, that takes in test data, does two different things with them in a sense, and then checks that the law, the general property, holds. Now when we have these function and we compile it, we have it in some form so we can run it, we can now input a lot of different x in the first one and check that this holds. And the more time we have, the more different x we can generate and be more sure that this will hold forever for all data. Or if it doesn't, we will find the problem maybe. The second one, generate two lists. And so you see here that in this short description, the types are not there. So typically in programming languages, if you do this, you would have to express the types, and the system would use the type information to know what kind of data to actually generate and put in there, right? So when you have these properties, the small pieces of code, in Quick Check you can send that to a Quick Check function. So main is just the REPL, the way you interact with the Haskell system. Quick Check is a call to the Quick Check tool. So it's a function in the API of the Quick Check tool, and you give it simply a property. And now using Haskell type inference and so on, it will see what do I need to generate in order to test this property. And in the default setting, it will run it 100 times. So it will generate 100 different, or 100 the same. I mean, that depends on how complex the data type is. It will generate 100 datums, and it will run the property on that data 100 times. But of course, you can run this 1,000,000 or 1,000,000,000 times if you have the time. So the interesting case is now if the law fails. So to illustrate this in the paper, they write a property which is wrong. So this is not typically what would happen, right? But this is a way to show what can happen. What typically would happen is that we write the properties correct, but the code we're testing is not correct. So those would be a little bit different. But here, they've written the second law, I think, in the wrong way. So they look at on the left side in the property rev app, it takes in two sequences again, and it concatenates them and reverses that. But on the right side, you see they forgot to reverse the order, right? So they reverse the first one and then concatenate with the reverse of the second one. So this is actually not a law that we expect to hold. But this can happen, right? You write code conditions and you might do an error when you do that. So what would happen if we run this to a good quick check tool? Yeah, so you see we invoke the quick check function in the same way. We give it our new property, and then it says I can falsify the property. I can give you an example of test data where the property does not hold. It is false. So we can falsify it. And here you see the two data that would falsify it. So now we can check it in our heads. XS is an array with the single value, and that value is 2. And YS is an array of two values. And in this case, they are -2 and 1. So we try it up there. So if we concatenate them, we get a new array which has 2, -2, and 1. So it is a length 3. If we now reverse it, we expect to get a 1, a -2, and a 2, right? So that was on the left side. Let's try on the right side. We reverse excess. So that means reversing a list with a single element, so we get the same thing. So we have still there the 2. And then when we reverse the YS, we get a 1 and a -2, and we now merge that. So we have a 2 first. In the other one, we had the 1 first. So it is true that the property is falsified by this example. And the good thing is, this is typically what you need to do. And in reality, what happened is that the quick check function probably found a much more complex sequences or arrays. And then it tried to shrink them. And when it came to these two examples, it wasn't able to shrink them anymore. Because if this YS only have a single element, it could also work, right? So, okay, so it's not minimal, right? We can, as humans, we can come up with a smaller example where it would be enough to have an even shorter YS actually. But the values in the two lists cannot be the same, because then the property is actually true even though it's wrongly written. So, you know, these are the things you can explore. When you come into practice, it's not as easy as you can try any type of test data. Often you have conditions on the test data, and then you can have conditional laws. So this looks a little bit different because maybe not all of you are used to Haskell. But the basic idea is that some properties and laws only holds conditional on some constraints on the input data. So here, for example, if we are testing the max function, the max of two values x and y should be y only if y is the same as x or if it's larger than x. So that's a condition for this property to hold, is that y is larger than or equal than x. If y is smaller than x, actually max of x and y is equals x, so the property does not hold. And of course, most in code this can be easily written, and you You can even safeguard your properties by sorting values. So you can take the property you write takes in any two integers or floats, and then you can sort them, and then you can apply the property so that you know that you have an order, right? But you know, there are different ways of expressing this in different languages. Here in Haskell, it's basically we define the property max lower than equal so that it takes an integer, and then it has a property. This is details about the implementation in Haskell and the typing. We don't need to go into details there. The important thing is that the property max LE takes two arguments, x and y, and then it checks that if x is less than or equal to y, then this should hold, right? So basically the condition will act as a filter, and the rest will not be checked or will be assumed to be true if x is larger than y. If we're testing a property of an insert function, so insert is a function that takes a value and a list of values of that type, the type of the first one, and it inserts this, right? And then you can check that if the original list was ordered from low to high, so it was sorted, then when you insert, if this is how you define insert in your language, the new list should also be ordered. So then the condition here, this is a conditional property, and it's conditioned on the fact that we don't take any sequence or array in. It has to be an ordered one. So here you see that this one can be a little bit hard to generate data for, because generating a random array is not likely to give you an ordered or sorted array. So this is good that you can express conditions, but it might lead to quite inefficient testing, especially if you have very specific conditions that you need to be fulfilled. Okay, that was the same thing. So one thing you can that becomes important in these systems is to monitor the data, because since the data is not explicitly in your test code any longer, it's being generated by the testing tool automatically. It can be a little bit hard for you to understand, is the testing any good? I mean, you can run 1 million or 1 billion tests using Quick Check or similar tool, PBT tool easily, but are they any good, right? How would you know? Because you don't see the test data. You haven't explicitly coded them in there or written them in there. So one way you can do that is, so Quick Check, the Haskell tool has a classify function, which takes a predicate, so something that can be true or not, and then it labels things. So it will label data, right? So here's a more complex property now for insert. So it still takes one integer, one array of integers, and then it checks if the array is ordered. Then we check, the classify will check now by checking null, and null is the length 0, right? Because an array of length 0 is ordered by the definition. So if the length of the data, the array is 0, we classify this as something we call trivial, because we only want to test that once, in a sense, and only so classify, the first line will happen for all data. So when it's not null, so when the length is above 0, so there are some elements in the array, then it will not be classified as trivial, so it will just be unlabeled. And then we go on to write the property on the next line. So never mind the $. This is Haskell specific. And then we have now, if it was ordered, then again, it should still be ordered after we do an insertion. So then when we run this property in the tool, it will say, okay, we tested 100 times. It seems to, or it holds. So it says, okay, right? But 43% of them were the empty array. So in some sense, they were all 43 test cases that were the same. So, you know, this is very important when you test for longer time and more complex situations, because if say 90, 99 or even more percent of your data is trivial, small, or the same, then your testing is not as good as you think. So this can be a practical tool. It's not really part of the key elements of the technique, but it is important to know about, because in practice you will need it. So how do you generate the data? We have talked mainly about the properties, not so much about the data. Of course, all PBT tools come with sort of the generate the code, or it supports the generation of the basic data types of the language, or the general basic data types like integers, floats, strings, arrays, and so on. And often you can combine them quite easily. So you can have like generators of the basic data, and you can put them together to quite quickly build up more complex data structures. So this is supported by all of them. So you can combine this with simple filters like the conditions, or you can do all kinds of like normal coding in your properties, if you will, to get data of certain size, or certain combination of sizes, or depth, or nesting, or whatever. But at some point you will have more specific needs, and then often these tools comes with a way for you to write your custom generator for data. And then it can be more or less random in a sense. When you write a custom one, you can say that basically you want to have arrays of a certain size, right? Or you can combine things in different ways. Maybe you want a tree or a graph with many nodes but very few edges, right? This will be hard maybe to generate in random, but you can do very specific things. Or maybe you want to generate graphs with separated clicks, right? So you have 3 different subgraphs in there, and you can come up with all kinds of situations where you will need to sort of steer how the data is generated. The actual way is a little bit hard for me to show, because that depends on the tool that you're using, but all of them have some support for this. But at some point you will need more advanced support for doing this. So some of the work I've done is about searching for specific test data instead. So you, rather than saying exactly how the data should be put together, you state what you want the data to look like, and we search for a generator that will give you that type of data. Or you can express things like you want a certain diversity, difference in your test data, and so on. So before I wrap this up, I want to show some industrial application. I will not go into the details here. I can just tell you, because I remember when they presented this paper. So they actually tested the Dropbox application, which is a way for distributed file synchronization. And they did this by having basically 2 different accounts with Dropbox, and both logged in at the same computer. And then they could run a property-based tester and write properties that they think should always hold, right? So if 2 users are sharing, having a shared file sharing area on Dropbox, when you put in files in one, you should be able to see them in the other in certain times. And if you put in the same thing at the same time, what will happen then, and so on. So the properties expressed a lot of the expectations you would have on this system, and then they just run it, right? They generate many combinations of actions, and in the end they found some bugs. And they did this as a case. They didn't have a formal connection to Dropbox at the time, but Dropbox, when they saw this, invited them to come there and show the work. So I think it actually helped fix a few bugs in Dropbox. Another case was testing AutoSAR software with Quick Check. So this is something used in the automotive industry to describe components. So you can imagine Volvo, they do not make every part of the car. They buy a lot from different manufacturers, and then many of these components have software in them, and everything needs to be able to integrate in the car. So AutoSAR is a way to specify what this component does, how it can communicate, what kind of data it needs, and what it can provide, and so on. So this case study was a larger one, and I think it was done together with Volvo Cars here in Gothenburg. So AutoSAR is a big document of like 3,000 pages of text specifying what AutoSAR components need to do and how they do it. So they translated this document into quick check properties. I think it was done in the Erlang tool, so it wasn't done in Haskell. Doesn't matter. The key thing is that then they did random test case generation and checked these properties, and they found over 200 issues. Not only with Volvo's part of this, but also with vendors, right? So they found many violations. And in the paper they show that the volume of these properties were quite small, and they could still find a lot of problems. So they argue that it was cost efficient or cost effective. Anyway, that was an introduction to property-based testing. In the assignment, you will do a little bit just to try this out with some PBT tool. And yes, that was all for today. Thank you.